During this module, we'll be discussing chapter number 4, Atoms and Elements. By the end of this chapter, you will be able to recognize that all matter is composed of atoms. You'll be able to explain how the experiments of Thomson and Rutherford led to the development of the nuclear theory of the atom. Describe the respective properties and charges of electrons, neutrons, and protons. You will be able to determine the atomic symbol and atomic number for an element using the periodic table. You also will use the periodic table to classify elements by group. Also, you will be able to determine ion charge from numbers of protons and electrons, determine the number of protons and electrons in an ion, determine the atomic numbers, mass numbers, and isotope symbols for an isotope, determine number of protons and neutrons from isotope symbols, and also calculate atomic mass from percent natural abundances and isotopic masses. Let's imagine that you are on Galveston Beach. What can you see? What can you smell? Maybe you would see some waves, sand, rocks, and if you're lucky, maybe even a whale. And what about the smell? It may smell like fish or salt. Let me tell you something interesting. Atoms are the foundation of our sensations. Typical seaside rocks are composed of silicates compounds of silicon and oxygen atoms. Seaside air contains nitrogen and oxygen molecules. Remember that we can find oxygen in nature as a molecule of O2. The same is with nitrogen. In the nature, we can find nitrogen as N2. Usually, the nitrogen is represented as in blue, as we can see here. These are molecules of N2 of nitrogen, and the red one is oxygen, O2. Also, seaside air may contain substances called amines. The amines are chemical compounds that contains at least one nitrogen in combination with hydrogen and carbon. And basically this is this representation of one amine. We can see here one nitrogen in blue, and the black spheres represent carbons while the white one represents hydrogen. So most of the times that we can find a molecule with one nitrogen and carbons and hydrogens, those are known as amines. The amine shows here basically is triethylamine is emitted by decaying fish. Triethylamine contributes to the fish's smell of the seaside. Now let's talk about the atom. How many atoms are in a pebble? Atoms are incredibly small. A single pebble from the shoreline contains more atoms than you could count. The number of atoms in a single pebble far exceeds the number of pebbles on the bottom of San Francisco Bay. And what about the size of the atom? To get an idea of how small atoms are, imagine this. If every atom within one small pebble were the size of the pebble itself, the pebble would be larger than the Mount Everest. Now let's talk about some facts of atoms and elements. Atoms compose matter. The properties of atoms determine the properties of the matter. An atom is the smallest identifiable unit of an element. An element is a substance that cannot be broken down into simpler substances. There are about 91 different elements in nature, and consequently about 91 different kinds of atoms. Scientists have succeeded in making about 20 synthetic elements not found in nature. The exact number of naturally occurring element is controversial because some elements previously considered only synthetic may actually occur in nature in very small quantities. The concept of atom is known since ancient Greece. Democritus and his mentor Leucippus record ideas of atoms. Democritus suggested that if you divide matter into smaller and smaller pieces, you end up with tiny indestructible particles. Democritus called them atomos or atoms, meaning indivisible. Democritus is the first person on record to have postulated that matter is composed of atoms. Here we have a picture of Democritus with Diogenes as imagined by a medieval artist. Even though Democritus established the presence of the atom in matter during this era, it is not until the 1800s that a physicist named John Dalton introduced what is known today as the atomic theory. In 1808, over 2,000 years later, John Dalton formalized a theory of atoms that gained broad acceptance. Dalton's atomic theory has three parts. Each element is composed of tiny indestructible particles called atoms. Second, all atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. And number three, atoms combine in simple whole number ratios to form compounds. Those are the three parts of the Dalton's atomic theory. Year passed until the English physicist J.J. Thomson introduced the concept of the electron. He discovered a small negative particle, which he called the electron. These particles are much smaller and lighter than the atom. They are uniformly present in many different kinds of substances. Thomson proposed that atoms must contain charge, positive charge that balance the negative charge of the electrons. The model that he established to represent the atom is known as the plum pudding model, where the negative charges, here represented in yellow, were held in a sphere positive charge that is represented in red. So the sphere has a lot of positive charge, while the electrons are the small particles with negative charges. In the 1900s, Rutherford did an interesting experiment known as the Rutherford gold foil experiment, where tiny particles called alpha particles were directed at a thin sheet of gold foil. Most of the particles passed directly through the foil. A few, however, were deflected, some of them at sharp angles. With these results, Rutherford discovered the atomic nucleus. So here we have the source of those alpha particles. Here we have the gold foil, and the particles were direct to that foil. And the thing is that some of them go through the foil, but other ones were deflected, or even basically return when they hit that gold foil. Now, let's remember that the atomic model at this time was the plum pudding model. And his expectation were that the alpha particles would pass right through the gold foil with minimal deflection. He thought that these alpha particles that has no any type of non-charges, they will go through that model. But what he observed was that a small number of alpha particles were deflected or bounced back because of this atomic particle that he named the nucleus. So basically, because he observed that there was this deflection or also this rebounding of those particles, he thought that there was some other particle in that model that when the alpha particle hit, it rebounds and make the alpha particle to deflect. And he called that small atomic particle the nucleus. This Rutherford's statements regarding the nuclear theory of the atoms. Most of the atoms, mass, and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space through which the tiny negatively charged electrons are dispersed. The number of negatively charged electrons outside the nucleus is equal to the number of positive charged particles, known as the protons, inside the nucleus, so that the atom is electrically neutral. In this image, the nucleus is greatly enlarged, and the electrons are portrayed as particles. The electrons are dispersed through a large volume but weigh almost nothing. So basically, this whole thing is the atom, and we have in the middle the nucleus, and all around in that space, you can find basically the electrons. The protons are here in the nucleus, and the electrons all around the nucleus. Now, let's talk about the mass of the atom and its distribution. The dense nucleus makes up more than 99.9% of the mass of the atom, but occupies only a small fraction of its volume. The electrons are distributed through a much larger region but don't have much mass. Matter at its core is less uniform than it appears. If matter were composed of atomic nuclei piled on top of each other like marbles, it would be incredibly dense. A single grain of sand composed of solid atomic nuclei would have a mass of 5 million kilograms if those atoms were basically very dense. So if those, because of that large area around the nucleus, it makes that the atoms are not that heavy, so the mass will be more manageable. Astronomers believe that black holes and neutron stars are composed of this kind of incredible dense matter. The size of subatomic particles are different. If a proton had the mass of a baseball, an electron would have the mass of a rice grain. This is basically the mass of the electron. This is a comparison between the mass of the electron and the mass of the proton. So the proton is nearly 2,000 times as massive as the electron. What about the charges of the subatomic particles and their behavior? Electrical charges or electrical charge is a fundamental property of protons and electrons. Positive and negative electrical charges attract each other. Positive, positive, and negative charges repel each other. Positive and negative charges cancel each other so that a proton and an electron, when paired, are charge neutral. But it is important to understand that even though the charges are cancelled, it doesn't mean that the subatomic particle lost their corresponding charge. Here we have a table that summarizes the properties of the subatomic particles. Here we have the charges associated with each subatomic particle. Proton, positive or positive 1. Neutron is a 0, doesn't have charge, is neutral. And the electron, that is -1 or negative. As we can see, the mass of the protons and the neutrons are very similar, while the mass of the electron is almost negligible. Matter is normally charge neutral, having equal numbers of positive and negative charges that exactly cancel. In an electrical storm, the charge balance of matter is disturbed. This discharge occurs between electrical charge regions of a cloud, between two clouds, or between cloud and the ground. In this example, we are looking at this charge from the cloud and the ground. Sometimes that this charge is between the same cloud or also between clouds and cloud. So we have three different type of discharge. But you can see that lining that it represents that the matter is rebalancing. Now, what is the difference between an atom and an element? Elements are defined by their numbers of protons. It is the number of protons in the nucleus of an atom that identifies the atom of a particular element. If an atom had a different number of protons, it would be a different element. The number of protons in the nucleus of an atom is its atomic number, and it's given the symbol of Z. So Z is the atomic number of each element. Each element has a specific atomic number that also represents the number of protons in the nucleus. Here we have an example of two different elements, helium and aluminum. Here we have that in the nucleus, helium has 2 protons, so the atomic number for helium is 2, while aluminum has 13 protons in the nucleus, so that's why the atomic number for aluminum is 13. And because we're talking here about elements, the elements are neutral, so that means that in the nucleus we have 13 protons, and all around the atomic cloud we have 13 electrons. The same way with the helium. In helium, we have 2 protons in the nucleus, and we have 2 electrons all around the cloud of the atom, okay? Because it's a neutral, we're talking here about elements, and when we're talking about elements, all of them are neutral. They have the same number of electrons and protons, so they can cancel each other. And that's why what make the elements different, because they have different number of protons. The atoms all has the same thing: protons, electrons, and neutrons. The elements have the same thing but in different ratios. Helium has 2 protons, 2 electrons. Aluminum has 13 protons and 30 electrons. So that's why the elements are different. Here we have a periodic table where we can find a lot of valuable information. Not all of the periodic tables have the same information format, but most of all have the same information. Each of these squares right here represents or has an element and their basic information. For example, the symbol, the chemical symbol in this case is Be. Also, we have the name, beryllium. We have the atomic number, represent also as a Z. Remember that this is the atomic number of this element that also represents the number of protons. And here we have the atomic mass for the element. So each square represents an element with that information. You can have maybe a different periodic table, but most of the time that this is the basic information that you will have, maybe in different range. Sometimes the name is at the top, or the atomic number is on the right side or the left side. So it all depends, but the information is going to be always there in that square. We're going to go into more details of this periodic table in a little bit later. So for now, the question will be where those names of those elements come from. Most chemical symbols are based on the English name of the element. Some symbols are based on Latin names. The symbol for potassium, that is K, is from the Latin kalium, and the symbol for sodium, that is Na, is from the Latin natrium. So that's why potassium is K, because that K comes from the Latin name of potassium, that is kalium, and the Na from the Latin number natrium for sodium. Additional elements with symbols based on their Greek or Latin names include the following. So we can have here the lead, mercury, iron, that sometimes we can see that other elements, for example, hydrogen H, carbon C, so they are like, okay, we have the name, we have the symbol, and it's basically the first letter. But sometimes we have different names with different symbols, and it's because we are using the symbols from the Greek or the Latin. Also, I would like to highlight that when the symbol is just one letter, we must write it as a capital letter here as the potassium, that we have a capital K. But you can see when you have two letters in the symbol, the first one must be capitalized while the second one must be in lowercase. Always. We can see here the sodium and A, capital letter, lowercase, silver A as a capital and G as a lowercase. So always when we have just one letter, it's going to be capital letter. When the symbol of the elements has two letters, the first one is going to be a capital and the second one is going to be in lowercase. Early scientists gave new discovered element names that reflect their properties. Argon, from the Greek argus, means inactive. So basically they found that this element that was inactive, and because it was inactive, they called them argus and eventually became argon. Other elements were named after countries. Polonium from Poland, francium after France, and americium after United States of America. Other elements were named after scientists. Every element's name, symbol, and atomic number are included in the periodic table and in the alphabetical listening also in this book. There are other very interesting names for elements. For example, the curium is named after Marie Curie, a chemist who helped discover radioactivity and also discovered two new elements. Curie won the two Nobel Prizes for her work. Also, bromine originates from the Greek word bromos, that means stench. Bromine vapor, seen as the red-brown gas in this photograph, has a strong odor, so that's why the name bromine comes from. Another good question is why the periodic table has the arrangement as a table. So Dmitry Mendeleev, a Russian chemistry professor, proposed from observation that when the elements are arranged in order of increasing relative mass, certain sets of properties recur periodically. So initially, he puts all the elements like in a row, as we can see here, where the color of each element represents its property. Now, we can observe that, for example, the green one repeats also here, the pinkish one here, the orange also here. So you can see that there's a pattern, okay, in when the property is repeated. So he arranged basically the list in a way that all the elements that have the same properties were in the same group. So now we have all the pinkish here, the green, the orange here, the blue here, the green here, the white here in the middle. So this figure is similar to the Mendeleev's first periodic table. Mendeleev's periodic table was based on observation. Like all scientific laws, the periodic law summarized many observations but did not give the underlying reason for the observation. Only theories do that. For now, we accept the periodic law as it is, but in Chapter 9, we will examine a powerful theory that explains the law and gives the underlying reason for it. So, the elements in the periodic table can be broadly classified as metals, nonmetals, and metalloids. Using the periodic table, we can identify each element as one of those groups. If it is a metal, a nonmetal, or a metalloid. For example, first of all, we can see here a black bold line, okay, like a ladder. All the elements that are from the left side are classified as metal, with these three exceptions. But all the other that are basically in this yellowish color, all of these are basically metals. From the right side, the greenish one are classified as nonmetal, including the hydrogen. Okay, and the elements that are basically at the right side and left side directly to the letter in contact with that letter are known as metalloids. You may ask why the hydrogen is greenish and is basically in the area of the metals. And we're going to understand that a little bit later when we talk, I mentioned before about chapter 9, that we're going to explain a little bit more why, for example, this case of hydrogen, even though it's in the first group that it will be maybe classified as a metal, the hydrogen itself is the only one that will be classified as a nonmetal. So for now, from the right side of the ladder in greenish, all the nonmetal. From the left side, all the yellowish are metals, with the exception of hydrogen. And we're going to have this group that are directly in contact with the ladder, okay, that are known as the non as the metalloids, sorry, as the metalloids. So let's talk about the metals, some characteristic and properties of the metals. Metals occupy the left side of the periodic table, as I mentioned before, and have similar properties, which are that they are good conductors of heat and electricity. Also, the metals can be pounded into flat sheets. This is called the malleability. Metals can be drawn into wires that's known as ductility, and also they are often shiny or lustrous. Okay, so these are three very important characteristics of the metal: malleability, ductility, and lustrous. Metals tend to lose electrons when they undergo chemical changes. Good examples of metals are iron, magnesium, chromium, and sodium. So what about the nonmetals? The nonmetals occupy the upper right side of the periodic table. The dividing line between metals and nonmetal is the zigzag diagonal line running from boron to acetine. Nonmetals have more varied properties. Some are solids at room temperature, while others are gas. As a whole, nonmetals tend to be poor conductors or heat and electricity. Sorry, they are poor conductors of heat and electricity. The nonmetals tend to gain electrons when they undergo chemical changes. So the metals will lose electrons in a chemical change. The nonmetals will gain electrons if they undergo a chemical change. Good examples of nonmetals are oxygen, nitrogen, chlorine, and iodine. And now the metalloids. Metalloids lie along the zigzag diagonal, as I mentioned before, line dividing the metals and the nonmetals. They are also called semi-metals and display mixed properties. For example, metalloids are also called semiconductors because of their intermediate electrical conductivity, which can be changed and controlled. This property makes semiconductor useful in the manufacture of electronic devices that are central to computers, cell phones, and other modern gadgets. Silicon, arsenic, and germanium are good examples of metalloids. Here we show a plaque of silicon, okay, a good semiconductor. The periodic table can be divided in two big groups: the main group element and the transition series of elements. The main groups are here represented by yellow. Here we have two main groups, and here we have six main groups. They have assigned a number for each group: group 1, group 2, group 3, but also a letter. So this is group 1A, 2A, 3A, 4A, and so on. Meanwhile, the transition metals, that are this one here in blue, also they have assigned a number and a letter. The transition metals are in the letter B, but with the same number 3, 4, 5, 6, 7, while the main element group elements are with the number and the letter A. In the main group elements, properties can generally be predicted based on the element's position. So if we know the position of some of these elements, we can have some idea of the properties of those elements, of that element specifically. While in the transition metals, properties tend to be less predictable based on the element's position. Some of the main group's elements have common names. For example, the group 1A is known as alkali metals. The group 2A is known as the alkaline earth metal. and the group 7A, the halogens, and the 8A is the noble gases. So basically, those are four of the main groups that has the specific names. Also, I would like to highlight that there are two groups from the transition metals that you'll see like outside, okay, are this one from the periodic table, but they are part of it. They are known as the lanthanides, that is this group, and the actinides, this one. These two groups are supposed to be in this area. So the lanthanides are supposed to be between the 57 and the 72, and the actinides between the 89 and the 104. But the thing is that if we put all this element right here, that will affect the range of the other main groups. So that's why most of the time, even though they are here, these are the location of those transition elements, you're going to see them most of the time outside of the periodic table, but they are part of it. The alkali metals include lithium, that is this one that we can see here, as well as sodium, potassium, rubidium, and cesium. The alkaline earth metals include beryllium, magnesium, that is right this one right here, calcium, strontium, and barium. As you can see, they are pretty reactive. And also they are like solids because they are metals. The halogens includes the fluorine, the chlorine, bromine, iodine, and acetine. So here we have chlorine as a gas, and also the iodine here. It is a gas, but also when you can make the position, you can see the solid of the iodine. The group of the noble gases includes helium, neon, argon, krypton, and xenon. Now, what happened in a chemical reaction? In a chemical reaction, atoms often lose or gain electrons to form charged particles called ions. So to produce an ion, the only thing that you need to do is to lose or gain electrons. You don't lose or gain protons, because if you lose or gain protons, you become another element. Remember that the number of protons is specific for the element. So hydrogen has just one proton, helium 2. So if you remove one proton from helium, you become a hydrogen. Okay, so that's why when you are creating ions, you are losing or gaining. You're going to add or remove electrons from the specific element. So positive ions are called cations. Negative ions are called anions. The charge of an ion is shown in the upper right corner of the symbol. Ion charges are usually written with the magnitude of the charge first, followed by the sign of the charge. For example, magnesium 2 plus, oxygen 2 minus. So here, the magnesium, to become a positive ion, it loses 2 electrons, while oxygen, to become an ion, it gains 2 electrons. So remember, the only thing that you lose or receive or give to produce an ion in an element is going to be electrons. Let's see some examples. In reactions, lithium atoms lose one electron to form lithium positive 1. So here we have lithium as an element, but in a reaction, chemical reaction, it loses one electron, so that's why it becomes a positive ion, also known as a cation. The charge of an ion depends on how many electrons were gained or lost and is given by the following formula. We have here the number of protons minus the number of electrons. The number of protons, remember, that also is the atomic number, the one that represents the specific element. So where P positive stands for the proton and E negative stands for the electron. For lithium plus 1 ion with 3 protons and 2 electrons, the charge will be 3 minus 2. 3 protons, or the atomic number of lithium, minus the 2 electrons that it will have at the end of the reaction. so it will become 1 plus. What happened when an element gain an electron? For example, fluorine. Fluorine most of the time is going to gain 1 electron, so that's why when is an element is neutral, it doesn't have a charge, but if you add 1 electron, it becomes fluorine minus 1. The charge of an ion depends on how many electrons were gained or lost, as we mentioned before. So the following, the same um, formula. And fluorine has 9 protons because the atomic number of fluorine is 9, minus 10 now because we add 1 electron. That's why the ion of fluorine or the anion of fluorine is 1 minus. That's the charge of the anion of fluorine. The number associated with the letter A above each main group column in the periodic table, 1 through 8, gives the number of valence electrons for the elements in that column. Those valence electrons are the most exposed electrons on an atom. They are the ones that you can share or you add more electrons in that area. So they're called the valence electrons. The key to predicting the charge acquired by an element is its position in the periodic table relative to the noble gases. Main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. As we can see here, we have from family 1, all the ions are cations and they are 1 plus 1. From group 2, all of them can form cations 2 plus. From group 3, all of them can form cations 3 plus. All of these elements here, they have in common that they are metals. So as you can see, all the metals will always form cations. From group 1 to group basically 6AA, you can form all of them cations. You can have from the metals are the sources of the cations. On the other hand, you can see here from group 5A, 6A, and 7A, these are the nonmetals and they have negative charges. So the nonmetals will produce the anions. In the case of nitrogen, family 5 is going to be 3 minus. Oxygen minus 2 or 2 minus, and all the family of 6A are 2 minus, and the halogens is going to be minus 1 minus, okay, because this one are gaining electrons, this one are losing electrons. In that way, fluorine has just 7 valence electron, fluorine the element, but if it gains 1, it will have 8, and it will be similar to this halogen. Okay, it's the same thing with nitrogen. Nitrogen, because it's in family 5, it has just 5 valence electrons. So it needs 3 electrons. That's why nitrogen, it will gain 3 electrons. So in that way, now as an ion, it will have 8 electrons in the valence. So that will be similar as this halogen. So all of the ions, they want to have the same number of valence electrons as the halogens. Sodium, for example, is plus 1 because it's more easy to lose 1 electron and have become this has this number of valence electron than gain 7 electrons, because if he wants to be like this one here, it will need to gain 7 electron because he just has just 1 electron, so it will be need 8. So it's more easy to lose 1 electron, get rid of 1 electron, than gain 7 electrons. So that's why it's more easy for the metals to lose. The same thing with calcium. Calcium is from family 2, so that means that it has 2 valence electrons. So if he wants to become or have the same configuration of the halogens, it will need to or add 6 electrons or lose 2 electrons. So it's more easy to lose 2 electrons. That's why all the cations produced from family 2 will always be 2 plus. From family 1, 1 plus. From family 7, because we have 7 valence electrons, it will be more easy to gain 1 than lose 6. So that means 7. So that's why all the anions from family 7 will be always 1 minus. That's the same thing with family 6 will be 2 minus. So, all atoms of a given element have the same number of protons. Remember that if you have the same number of protons for different atoms, they are the same elements. If you have different number of protons, you're talking about different type of elements. Okay, so all atoms of a given element have always the same number of protons. They do not necessarily have the same number of neutrons. Okay, they will always have the same number of protons, but not necessarily the same number of neutrons. Atoms with the same number of protons but different numbers of neutrons are called isotopes. So isotopes are elements with the same number of protons but different numbers of neutrons. All elements have their own unique percent natural abundance of isotope. So let's see the following example of isotopes. Neon. Neon, basically naturally occurring neon, contains three different isotopes. The first one is known as neon 20 because it has 10 protons and 10 neutrons. The second one it is known as neon 21 because it's neon, it has to have the same number of protons as the one before because it's the same atom. So we have 10 protons but 11 neutrons. And for neon 22, we may have 10 protons and 12 neutrons. Okay, so between an element, if we have different isotopes, we're going to have those isotopes are going to have always the same number of protons but different number of neutrons. And also, their natural abundance is going to be really different from the other one. So, for example, here the neon 20, okay, has a 90.48% of abundance naturally, while the neon 22 occurs in 9.25% of the times, and neon 21 just 0.27%. So basically, that means that if we have 100 atoms of neon, 90 are going to be, for example, neon 20, while 9 are going to be neon 22, and just one or less than one is going to be neon 21. Okay, so that's basically what this means. This means that in 100 number of atoms, you're not going to have always 100 with the same isotope. If you have different isotopes, you're going to have a specific number of each of them. So for once again, for neon, if we have a sample of 100 of atoms of neon, 90 of them are going to be neon, the isotope of neon 20, because neon 20 exists as natural as 90.48%, while neon 22 exists at 9.25, close to 9%. So that means that from 100 you will have 9 atoms as an isotope of neon 22, and for neon 21 is going to be one atom at least from that 100 sample that you have of atoms from neon. Isotopes are often symbolized in the following way. Here we have A, Z, and X, where X is going to represent the chemical symbol of that isotope. The A, letter A, this number is going to be a number, is going to represent the mass number, and this other number that is represented here by as Z is the atomic number of the element, okay, that this also represent the number of protons, okay? So here we're going to have the number of protons, here we're going to have the symbol, chemical symbol of the element, and here we're going to have a new definition or a new information that is known as a mass number represented by a letter A. But remember that both of these are numbers, okay, and this is going to be at least one or two letters. It all depend on the element. So for example, for neon, if we're going to represent this one using this representation, neon 20 is going to be neon, the 20 and the 10 here. The 20 is a mass number, and the number 10, the atomic number, the number of proton. For neon 21, the mass number is going to be 21, and the atomic number 10, because we're talking about neon. Neon has atomic number of 10 proton, as well as with neon 22. Okay, so this is this representation of the three isotopes for neon. So the mass number, represented by as the letter A, is the sum of the number of protons and the number of neutrons. Okay, so the mass number is going to be equal to the sum of the number of protons, or the atomic number, and the number of neutrons. The number of neutrons in an isotope is the difference between the mass number and the atomic number. So if we want to determine the number of neutrons, we're going to subtract the mass number and the atomic number. So a second notation for isotopes is the chemical symbol or chemical name followed by a hyphen and the mass number of the isotope. So here we have the chemical symbol and here the mass number to make the difference between the three different or more. One element could have at least maybe 6, 7, 10 isotopes. It depends on each element. So here for neon, we're just going to have 3 isotopes. Neon 20, neon 21, neon 22. You can represent it as just Ne20 and E21 using the symbol, the chemical symbol, or the name. So neon 20, neon 21, neon 22. Remember that from the name or the symbol, you can determine, if you go to the periodic table, the atomic number. So the mass number minus that atomic number is going to give you the number of the neutrons. Okay, so remember that you don't need here basically the atomic number, because from here, from the element, the symbol, or the name, you can find the atomic number in the periodic table. Now let's talk about the atomic mass. The atomic mass of each element listed in the periodic table represent the average mass of the atoms that compose that element. Remember that when we talk about the atoms, we are talking about the isotopes. For example, chlorine consists in 75.77% of chlorine 35, which has a mass of 34.97 atomic mass unit, and 24.23% of chlorine 37 with a mass of 36.97. So the element of chlorine has 2 different isotopes, chlorine 35 and chlorine 37, with a specific percent of natural abundance and also specific atomic mass. So its atomic mass can be calculated as the following. We need to change that percent to the decimal. So that natural abundance always, most of the time, is going to be represented as a percent. So we're going to change that percent to the decimal, dividing this percent by 100. Okay, and we're going to find that 75.77 divided by 100 is 0.7577. And this abundance, decimal abundance, we're going to multiply by the atomic mass of that isotope, as well as the second isotope. The second isotope has a natural abundance of 24.23%. So we divide that by 100 and we'll have 0.2423 times the atomic mass of that isotope. And at the end, we're going to find that the atomic mass for chlorine is going to be 35.45 atomic mass unit. Okay, so once again, the atomic mass of any element is going to be the contribution of the different isotopes that element has. So for example, chlorine has 2 isotopes, chlorine 35, chlorine 37, and a specific natural abundance. So we need to be careful when we're working with this type of problems, that we need to identify each natural abundance and the atomic mass for each isotope, change the percent to the decimal, multiply by the atomic mass of that isotope, and then we can add all the different products for each of the isotopes, and that will give us the atomic mass of that element. So in general, atomic mass is calculated according to the following equation. The atomic mass is going to be the fraction of the isotope. This is the decimal part, okay? If we have the natural percent, we divide by 100 times the mass of the isotope, okay? So if we have 5 different isotopes for the same element, we're going to do this 5 times. The fraction of isotope 1, 2, 3, 4, 5, multiply the 1 by the mass of isotope 1, the fraction of isotope 2 with the mass of isotope 3, and so on until we have calculate all the products of each of the isotopes of the specific element. where the fraction of each isotopes are the percent natural abundance converted to their decimal values. So let's do the following problem. We have gallium has two natural occurring isotopes. So we have two isotopes for gallium. Gallium-69 with the mass of 68.9256 atomic mass unit and a natural abundance of 60.11%. And gallium-71 with a mass of 70.9247 atomic mass unit and a natural abundance of 39.89%. So we need to calculate the atomic mass of gallium. To do this, we need to first change the percent to the decimal expression. So we're going to divide each one by 100. So for gallium-69 that has a 60.11% of abundance, we divide it by 100, and we're going to have 0.6011. Okay, while for the gallium-71, we divide the abundance, that is 39.89% divided by 100. That will be equal to 0.3989. So now this decimal, we need to multiply this by the atomic mass of the first one, 0.60, while the atomic mass of gallium-69, and 0.3989 with the atomic mass of gallium-71. So that means that we have this 0.6011 times the atomic mass of the first isotope, gallium-69, and for this one, gallium-71. So now, once we multiply, when we have the product of each of the multiplication, we have this, then we add those two quantities, and we're going to have finally this result. But remember that we need to talk and we need to be careful with the significant figures. So here we have 4 significant figures. We have here 6. So because it's a multiplication, now we need to express at the end the result in 4 significant figures. Okay, so that means that we have a 69.72 atomic mass unit. Some isotopes are radioactive. The nuclei of some isotopes of a given element are not stable. Because of that, these atoms emit a few energetic subatomic particles from their nuclei and change into different isotopes of different elements. So that means that if you have one element that is radioactive and this element react and release some kind of energetic subatomic particle, it will turn in a different element, okay, when that happens. The emitted subatomic particles are called nuclear radiation, and the isotopes that emit them are termed radioactive. Nuclear radiation can be harmful to humans and other living organisms because the energetic particles interact with and damage biological molecules. Some isotopes, such as lead-185, emit significant amounts of radiation only for a very short time. Other isotopes, as plutonium-239, remain radioactive for a long time, thousands, millions, or even billions of years. But not all the radioactive isotopes are harmful. Many have beneficial uses. For example, technetium-99 is often given to patients to diagnose disease. The radiation emitted by technetium-99 helps doctors image internal organs or detect infection. So radioactive elements are really, really important also. They are not always used to harm, to make damage, but also sometimes they are used to, as we can see here, beneficial use for medicine and to detect some infection, and we can have a better look of what is happening with the patient. So that's why also radioactive isotopes are really, really important. So this will be all with chapter 4, atoms and elements.